Okay, everyone, welcome to class. So to get started, I'm told that I broke the reading assignment. Apparently, it was due at the wrong times. My bad. Last year, Danny took care of this, and I assumed that I was competent enough to assign these things accurately, and I probably mixed up my AMs or PMs or something. So don't worry, I'll set all these equal to, I can do two things. What do you prefer? They're really easy points, so should I reopen the quiz tonight and have it be open until next class period, so you can take it whenever you want? Get your 5 for easy points. Otherwise, I make them all worth 0, but let's pick up easy points. These are a cinch. Yeah. Which maybe it was because it's a hard one or something. Yeah. So I will fix that. In general, did we do them worth half a point, Danny, or were they worth 1 point last year? The reading quiz. I'll find out. I don't know what they're supposed to be. The point is they should be easy, and if they're anything other than that, or if like doing them online is hard, it's because I'm messing that up. So I'll get that fixed. Okay, so a couple announcements before we get started. First off, Monday's Labor Day, so you'll off be doing whatever you do on Labor Day, which means that's when we have 2 of our office hours, and it's kind of before the next homework's due. So our TAs are wonderful, and Elias, who's not here, but Danny, who is. Oh yeah, they're both here. They've both very kindly offered to hold an extra or an alternative set of office hours on Tuesday, right, the day before it's due. So Danny's will be from 11 to 1. I presume that'll be up in the 3rd floor of the CME building in that breezeway area, which is just right out of the elevator. If you haven't been up there yet, you take the elevator, and then you look to your left, and it's right there. Elias, you're going to be the same thing. So Danny's is from 11 to 1 p.m. Elias will be from 4 to 6 p.m. So that's very nice of them to offer those. Appreciate it, guys. All right, so the learning objectives for today are the following. First, we're going to calculate the theoretical and the experimental component of electrochemical voltage. So we already did the theoretical part last time. We're going to review it, but today we're going to introduce, all right, how does the experimental component, meaning what's actually there, change the voltage that you might observe? We're going to do lots of examples today, including some where the number of electrons involved in the redox and oxidation reactions are not the same. Maybe 1 is 1, 1 is 2. Like, how does that change things? Okay? And then the last thing is, if we have time, we're going to calculate something called the Pilling-Bedworth ratio, which is this pretty clever thing that helps us know whether something's going to oxidize once and then form a protective skin, or whether it's going to keep on oxidizing until it's eventually totally corroded. Okay? So last time, we talked about this standard reduction potential table, which was super helpful because it told us which thing gets corroded. For example, we said that if you partner iron up with zinc, then the zinc dissolves. But if you partner iron up with copper, the iron dissolves, right? And at first that seemed puzzling, but once we used this table, we said, oh, it makes sense because the one that's lower on this table, when it's written as a reduction potential, it's going to be the one that's lower is the one that gets flipped and becomes an oxidation. The reason it does that is because when you do flip it, this number associated with it, the voltage associated with it, the half-cell voltage, also gets flipped. And when you take, say, for example, zinc, which is negative 0.76, and copper, which is 0.34, you're going to flip this one so it becomes a positive 0.76. 0.76 plus 0.34 gives us about a volt. And we showed you with a pretty slick demo that when we take defaced pennies, which are zinc and copper pairs put together, and we stack, 5, 6, 7 of them together, we've now got a 5, 6, or 7 volt battery, right? Now, that battery is not capable of delivering current very efficiently because the contact between those pennies is pretty terrible. And for other reasons, there's corrosion on the surface and things like that. But it can technically produce that voltage. Like if you put a multimeter up to it, you would have seen, 5 or 6 volts on that thing. And it was clearly enough to light up an LED, which doesn't require a big current. Just a trickle of current can make those things light up. So we saw that. Okay? So when we wrote these things last time, we said, okay, copper and zinc. We flipped one of them, so this negative 0.763 became positive, and that's what gave us this number. This is what we call the overall cell potential. Overall cell potential. And again, I didn't pick that name because if I would have named it, I would have named it something else. Because overall cell potential sounds like you're done. Like that's the voltage you're going to get when you actually make a battery out of this. But that's not the case. It's definitely not the case, and here's why. We said that this is just like free energy. And in free energy, the overall change in energy had both the theory and the experiment component. And it's the exact same thing here. This time, well, first off, how do you convert between free energy and these voltages? There's a very simple equation. The change in the free energy, this is delta Rg naught, right? This is the theory part, is equal to negative N times F, where N is the number of electrons involved in your redox reaction. F is Faraday's constant, and then there's your overall cell potential. Okay? Now, we said before that it's just like it, that there's both experiment and theory. So here you see it. Here's our theory. And then this whole thing is the experiment part, right? And it looks really similar to the delta G expression, right? Delta G was delta Rg equals delta Rg naught plus RT natural log of Q. Well, this is different. It's minus because, again, in this expression up here, they're related by a negative sign. I didn't do it. Don't look at me, right? And then NF, right? Otherwise, it's the exact same. Now, how can we have this? We've got a concentration of the metal that gets oxidized raised to the number of electrons involved in the oxidation. And down here, we've got the concentration. That's what the square brackets means. The concentration of the metal that gets reduced, and it's reduced by however many electrons are involved in it, okay? So where is that coming from? In free energy, we had the nice reaction quotient, which was products over reactants. It made it really simple. This is the exact same thing. So if we look at our equation, right, for say copper and zinc. Copper and zinc, when we wrote the two half-cell reactions together, redox, right, reduction and oxidation, when we combine them, this is our reaction. There's no gases here. So we're not going to do the partial pressure of any gases here. Instead, remember last time we said that solids and liquids we ignore? That's not the case with dissolved metals, right? When there's a dissolved solid, we're going to include that, and we're going to use the concentration. So instead of using a partial pressure, we're going to do products over reactants, just like before. It's going to be the product of the concentration of the product raised to the number of, right, coefficient in front of it, the moles in front of it. We would exponent just like it before, divided by this species, the concentration of this one, raised to the exponent of however many coefficient, moles there are. Any questions on that? If this was written as a gas, it'd be straightforward. Since it's not gases, you need to take into account the concentration of these dissolved metals. Okay? It's still products over reactants, right? Now, in this one, I've written it as the concentration of the oxidized species over the reduced. That's simply because spontaneously, this will always be your oxidized species. This will always be your reduced species if this is a spontaneous reaction. Okay? Are there any questions on this, on how we went from free energy and we translated it over to electrochemistry? Yeah?
So last class you said that if that overall cell potential is negative, it won't be spontaneous.
Yep. If it's negative, that means that's the voltage that you would have to apply to this to drive that reaction, which you can do.
Okay, so
Like when they do electrowinning, electroplating, they apply a voltage to make something happen very often.
you said that you put the sign on the more negative one.
Yep.
So how would it ever be negative?
If you assumed it backward, well, we're going to show you an example. For one thing, there's two things. You could assume that it was one way and have it backwards, and then you add it up and realize you got a negative number and be like, oh, shoot, I guess I just had it backwards. So you rewrite the whole thing. But there's another way that it can get messed up, and that's because you have to consider both theory and experiment. This guy right here, this is your theory component. Maybe it's giving you a positive voltage, so you're like, huzzah, it's going to happen. But this could send you the other way, right? So that's the thing you have to consider. Okay? And in that case, the whole reaction would get flipped. So just like free energy, where we said that these two components can change the direction of it, the same exact thing here. Any questions? Yeah, Isaac.
So does it always choose the one with the largest potential change? Like, for example, if the battery put an acid in there, which is extra H pluses, so it would choose the copper ion, or I believe the copper ions to, instead of the hydrogen ions, right?
That's a really good question. What you're asking is, like, there's lots of different species that could be oxidized or reduced. Is that really what you're saying? Because there's, like, acid in there that could also, H plus could turn into H2 plus, H2 gas, for example. So the one that is more favorable will be the one that when you add together the redox, right, reduction and oxidation, gives you the largest delta V. That should be the one that's most favorable. The other one might also be happening to a lesser degree. We won't do an example of that in this class, but that could be happening. You could potentially have both of those occurring. But one's going to be favorable because it's more thermodynamically favorable. Good question. That's a really good question. Yeah. What's your name? Chase.
And I may have missed it, but what is the distinction between, on that equation you just showed us, the N plus, and then is that also electrons transferred except?
So first off, you don't need to plug in a number here. This is just telling you the species of it. And in our formalism, like we've got zinc 2 plus because it gave off 2 electrons. But there's other ones, right? If you look at this chart, here's potassium 1 plus, right? Adding 1 electron. So this would not be potassium 2 plus, it'd be 1 plus. It's just defining your species, right? You could write a generic expression here for all of these things that says a metal raised to the N plus N number of electrons will give you that metal. And so it's just writing it in a generic way as opposed to the divalent way or something. Yeah, Josh? Josh. Okay. So if I understood you right, let me make sure I got this right. You said, okay, you add up some combination of things, and it was negative, meaning not spontaneous. And then what was the second part of your question? Oh, yeah. So yeah, if you apply that same voltage to it, you don't make it happen. You make it reach equilibrium. If you want to make it happen, you apply an overpotential. You go above that. Yeah, great question. Yeah, you'd have to go above that. And obviously, the higher the voltage, the more the thermodynamic driving force for that to happen. But if you go too high, then there might be other reactions that start to take place, and you can get dielectric breakdown. You can get problems. So it's not like higher voltage is always better. If you guys go out and work for Kennecott Copper and you're refining copper from their ores, it's not like you just say blast it with a higher voltage. That might be actually really not the way to go. That will definitely not be the way to go. Okay, other questions? In fact, it's even more specific there because when they're refining copper metal, there's other species in the copper that they don't want, like tellurium and antimony. They're toxic. They make crappy copper. And if you go to too high of a voltage, they become favorable. And so you want to add just enough for copper to plate, but the difference in potential for the others to become thermodynamically stable are a little bit higher. So you got to go to a just certain low level without destroying them. Anyways. Other questions, or should we do some examples? Let's do some examples. Good idea. Okay, first off, lots of these are on YouTube. And remember, if you're not remembering where to find them, you can just scroll down to the bottom, and you would click Chapter 16 in this worked example problem videos. And I've got oodles of them here, and you can just click them and watch them. There's links in the notes that should work as well. Let's do one right now. Let's assume that we're going to do an example of something that's a redox reaction, where the reduction and the oxidation parts are using different numbers of electrons, because this is going to introduce a little nuance. So let's pick ones. What are we going to react together? Give me something. Okay, sodium and hydrogen have the same numbers. Let's not do that one. Oh, cadmium. Oh, yeah, perfect. Sodium is 1 plus, cadmium's 2 plus. Okay, so first off, which one's going to get oxidized? Which one's going to get reduced? Remember, these are written as reductions. If we flip it, then they become oxidations. Which one? Sodium's right here, negative 2.7 volts. Yeah. Or in other words, think about this. If you had the cell set up with this against the platinum and the 1 molar hydrogen acid, right? Hydrochloric acid, right? It would take 2.7 volts just to make this not happen. Right? It really wants to surrender its electron and become sodium plus. Yeah, so sodium's definitely going to get flipped, right? It's going to be the thing that gets oxidized. And cadmium is going to be the thing that gets reduced. So let's write them out. Cadmium 2 plus 2 electrons. Cadmium 2 plus 2 electrons gives us cadmium metal. Meanwhile, we're going to flip it. We're going to say that sodium metal, if you give it an electron, or is going to give up an electron to become sodium plus. Now, if we add these two together right now, we have a problem. In the past, when we did this with copper and zinc, when we added them up, the 2 electrons canceled out. Reactants, products, when we add them out, it's balanced, which it ought to be, right? If 2 electrons leave this species, travel through your circuit, and then get picked up somewhere else, it's balanced. Here, that's not the problem, or not the case. We have 2 to 1. So we're going to have to do something to these equations. First off, let's write down what the voltages are. V naught for the reduction, cadmium was negative 0.403. Okay? Negative 0.403. And then the oxidation potential for sodium, since it used to be negative 2.714, we're going to flip it, so that becomes a positive 2.714. Now, if we add these up, the electrons don't cancel out. So we're going to have to do something to this. We're going to have to multiply this equation by 2. Okay? Now, there's a big, big catch here that's different than thermodynamics. When we did Gibbs free energy, if we multiply one of our equations, then you would also multiply the change in the free energy, right? The change in enthalpy, entropy, we said that just gets multiplied. That is not the case with electrochemistry. It's not the case. You don't multiply it. That's always a little bit tricky to understand. Think of it like, the best way I think to explain this is if you've taken Arne Stolp's double E class, anybody taken that right now? Not yet? You will soon. He's great. He talks about voltage in terms of like water difference, right? Like if you have like a pressure of water, say for example you've got water at a high elevation and a low elevation, there's a pressure difference. You can think of electrical voltage in the same way. This potential for electricity is related to the difference in, right, the electric potential between those. So in this case, this is basically saying like the height of that waterfall the electrons want to go down off of. Like how much benefit is there for them to drop down? So when we increase the number of electrons by multiplying this by 2, we're not changing the height. It'd be like changing the flow of the current going off of it. It's increasing the number, but it's going off the same height. So however you want to remember it, for free energy, enthalpy and entropy, you would definitely multiply that for the reaction. You do not do it for electrochemistry. Okay? So this is going to become 2. We're going to multiply it all the way across. And now when we add these things up, what do we get? Well, we have 2 sodiums plus cadmium 2 plus gives us cadmium plus 2 sodiums 1 plus. Okay? Now the electrons cancel out. What would the overall cell potential be? Somebody add that up for me. Math. 2.311. Okay, everybody clear so far on this? Everybody with me? This is the overall cell potential. This is the theoretical. As it's written on paper, that's the voltage that you would get out of this battery. That's a pretty great battery. If you made a battery out of that, each couple is 2.3 volts. It's pretty awesome, right? Now, in practice, when you actually make this thing, you have to consider the experimental component, right? So what would the real voltage be? The real voltage, delta V, is equal to delta V naught minus RT over NF multiplied by the natural log of our oxidized species. That's sodium plus. So the concentration of sodium plus raised to the 2 power divided by the concentration of our cadmium 2 plus raised to the 1 power. Everybody see why this 2 exponent is there? Because in our equation, we had this 2 in front of that. Everybody follow that? Yeah, Carlos?
Alternately, can we use the equation that's in the book that has it already multiplied out if we're assuming it's at room temperature?
I wouldn't. Yeah, because that's assuming room temperature. I would just learn how to calculate these in your calculator. Is safer bet. It's just one less thing that could go wrong on a test or something. Everyone see where this came from? Again, if this was free energy, it was delta RG naught plus RT natural log Q. Here it's minus because that conversion going from free energy to volts, they switched the sign on us for no good reason. And you had to divide it by NF to get the right units. Where N is the number of electrons. In this case, what would the number of electrons be exchanged? 2. So you'd use 2 here. And then Faraday's constant's 96,500 coulombs per mole. Yeah, question? Okay, If this was, think of these as gases for a minute. If they were gases, we would have said, okay, that's a solid, that's a gas, that's a solid, that's a gas. And therefore, the two things we care about, products over reactants, would be the partial pressure of sodium raised to the 2, because that's the exponent, or that's the coefficient in front of it that becomes an exponent in the reaction quotient. So we're doing the same thing. These just aren't gases. These are dissolved metals. So we're using, instead of partial pressure, we're using concentrations. So put those in moles per liter, right, in molars. And then you raise it to the coefficient. Okay? Yeah, question, Sam?
Would you also think of it in terms of log rules?
In terms of what?
Log rules, where you're pulling that 2 up, where it could be in front of you filling it into the...
So we didn't show you where this came from. I skipped that step last time, how we derived this equation. If you want, maybe I'll post it. I don't think I'm going to go through it in class. But the way that we derived this, I think, is exactly what you're describing. I just skipped it because I'd rather do another example than a derivation. Yeah, Abby?
So, if a constant in product over reactant, how come for the product part we're not noting so we're doing 2Na plus on the top portion, but we're not adding CH12.
Sorry, I missed it. What?
So for cadmium.
Yep, cadmium. Cadmium 2 plus. You pick up 2 electrons, become cadmium metal.
How come we're not adding that on Na plus? Like, why aren't you including just the base metal without?
Oh, okay. So just like before, solids and liquids that are of pure substances, we assume that they have an activity of 1. Meaning, technically, they could be in here, but they would just be 1. But things that are not pure substances, like dissolved metals, I mean, if it was a gas, we'd use the partial pressure, but here we're using a concentration. Okay, good question. Is that any other questions? Yeah, what's your name? Braden. So if I told you that there, I could say, that's a good question. I think I have an example of that in a minute. So it's the concentration in molarity, which means you need the number of moles of that compound divided by the volume of liquid that it's in. So we haven't given you that in this problem, but I could have just as easily said, you've got 5 grams of dissolved sodium at the end of the day, right, in some liquid, and you've got 5 grams of this. You could turn those into concentrations, and you could see what now the real voltage is. Again, this is what theory says it should be, but the real voltage is going to get modified by this term, and it's going to go either up or down. Okay? Isaac?
So that term is to take into account the fact that it's not going to have perfect access to the ions it wants.
Yeah. Like, what if you start out this reaction? Yeah, let's say you make a battery out of this thing, okay? You assembled your battery, but when you assembled your battery, you didn't add any cadmium 2 plus ions, right? Well, in order for this battery to work, you have to have cadmium 2 plus ions to accept electrons from the sodium and turn into cadmium metal. If you don't have any of this, then that's going to change this term and produce it to give you a negative voltage, meaning not spontaneous. Yeah. So just like when we talked about the gasoline in the reaction chamber, if there's no gasoline to start with, you can't burn it and create CO2 and water. Same thing here. If you don't have a reactant to start with, the reaction can't happen. Even though on paper it looks like it ought to. Yeah, question? Why don't we multiply it by 2? Yeah. If this was free energy, we would have. We don't here because, so basically think of the voltage, like this reaction as it's written, think of it this way. How badly does sodium want to turn into sodium plus? That's dictated by fundamental chemistry, right? In the periodic table, we know due to its location, it's 1 element away from being a noble gas, right? So it would love to get rid of this 1 pesky electron and look like, I think, neon, or whatever it looks like. So that's something that we don't change by what we couple it up with. Like this driving force, thermodynamic driving forces, is just fixed, right? Now, if you multiply it by 2, you can change the number of electrons, but that's not going to change the driving force. It's just going to change the number of electrons involved. Does that make sense? That's why this doesn't get multiplied. It's a little tricky. In terms of free energy, we're talking about the total change in energy for some quantity of substance to change. So if you double the quantity, it's a state function, it increases with the amount of it present. It should also double, but that's not the case here with this. This is describing a potential for some individual reaction to take place. That's maybe the best way I can explain it. Other questions, Carlos?
So I have a question for
Yep.
the end equation that we were looking at.
Okay.
So normally when you're doing a reaction that has two different atoms, you put 2 for the end, right?
Two different atoms.
Or like if you have two reactants, like a reactant and an oxidant, then
Oh, okay.
2 for the end. Is there like a time where you put 3 or
Oh, sure. Let's do another one real quick. Okay, instead of sodium and cadmium, let's do aluminum and magnesium. Aluminum is 3+, magnesium is 2+. How would this one work? Let's write it out. So first off, magnesium is lower by a little bit. Both of these things really want to be oxidized, but magnesium more so than aluminum. So let's write them out. Let's do another quick example. So we've got aluminum 3+, picks up 3 electrons and becomes reduced into aluminum metal. Meanwhile, magnesium metal will surrender 2 electrons to become magnesium 2+. Right? If you added these up, the electrons don't balance, right? So we have to fix that. And the way that we fix that is by multiplying this top one and this bottom one by different numbers. We're going to look for the lowest common denominator, right? So we want it to become 6. So this gets multiplied by 2. This gets multiplied by 3. That leaves us with 2 3+ ions, plus 6 electrons, plus 3 magnesium metals, gives us 3 aluminum metals, plus 6 electrons, plus 3 magnesium 2+ ions. Now the electrons cancel out. That makes sense? Did I mess something up? 2 aluminums. Thank you. That makes sense, Carlos? So you could do anything you wanted. If I gave you like a 4-to-1, what would you do? You'd multiply the one that has 1 by 4 so that they could add up.
Okay, but in the equation, would you put still 2 or would you put 3?
Good question. So in our equation, the equation I think you're talking about is this one, the delta V equals delta V naught minus RT over NF, natural log of our, in this case, what is it? Concentration of magnesium, 2+ raised to the third, divided by our concentration of aluminum, 3+ raised squared. And what value would you use here for N? You would use 6, because in the balanced equation, it was 6 electrons.
So the previous one that we did would do 2?
2. That's right.
That's my question.
Straightforward? This isn't so bad, is it? It's pretty rad, actually. This allows you to design for new batteries. Why do we need new batteries, real quick? Do we need new batteries? We're running out of what? We're running out of energy. So energy is never destroyed nor created. We just convert it from one form to another. And we have this beautiful giant nuclear reaction in the universe happening, blasting us with light, right, the sun. So we could convert rays of sunlight from radiation, right, into electrochemical energy in batteries, and we do that all the time, right? If you're like a windmill, not a windmill, solar photovoltaic. Well, the sun does drive the wind, which drives the windmill. Anyways, a photovoltaic takes the rays from energy from the sun, and in chapter 12 we will learn how it does it. It's amazing, right? And it turns it into electricity, and we use that to charge a battery. Meaning we take something that's not spontaneous and we drive it the other way. Now we've charged our battery up so that when you want to use it in your phone, it spontaneously gives those electrons up and makes your phone turn on so you can snap a selfie or whatever. Or listen to the new Tool album. 13 years, they released a new album today. Is nobody else excited about this? You were 6 when the last one came out. Anyways. Okay. Any questions left on this before we move on? Yeah. Oh, right here you mean? If this was a 0 number? So don't plug in 0. Plug in a really small number. What would it do? What's natural log of a really small number? Very, very negative, right? So this term, you'd be a very negative number minus a negative number. So that'd become very, very spontaneous. Meaning if there's almost nothing here, then the reaction wants to happen. Which makes sense. If there's very few products, that should be a driving force to create products. Should we keep going? Let's keep going. If you got questions, I've done lots of examples. Check them out on the YouTubes. All right, how about this? Quick clicker question. So, arm your clickers. Okay, the question is this. If we take a metal out of an aqueous environment, because you probably are familiar, if you leave like a piece of metal in water, it's going to corrode. Maybe you've seen boats or docks or things like that. So the question is, if you take metal out of that aqueous environment, can it still guarantee that you're going to stop the corrosion? Will this guarantee the stop of corrosion? Yay or nay? Like if it's out of water, if it's not submerged in water, you take it out of the water, are you safe? Will it ever corrode? Or can it still corrode is the question. It can still corrode. Okay, we're going to close the poll. Get your answers in. Okay, closing the poll. Nobody frantically asking to stay. Okay, can corrosion... Yeah, this will not guarantee. So why? Right? We just said this whole thing that in order for corrosion to take place, we had to have something like this elaborate setup. They were dunked in solution. You had ions present. You had the salt bridge, right? So how does this happen if you don't have that, right? So let's show you an example of it. In air, things can corrode, and they do corrode. Oxidation in the gas phase is super common. If you've ever had to polish silver, right, because it got tarnished, does anybody ever do this? Every year I ask this, and like, no one's polished silver. Somebody has? All right, maybe you've polished the tarnish off of silver, right? What's happening here in most cases, it's forming either an oxide, or I think in the silver it's actually a sulfide that's forming, but your metal is reacting with oxygen to form a metal oxide. That's a very common form of corrosion that can happen outside of water. It doesn't have to be submerged in water, right? So what would be the oxidation and reduction reactions for that? So if this is our overall reaction, a metal combines with oxygen to form a metal oxide, just do the same trick as we did before. If you're trying to figure out the redox reaction, if it's not immediately obvious, then the first thing I would do is write the oxidation state above it, right? So the metal in the elemental state is not oxidized or reduced. It has no oxidation state. It's 0. Whereas, and oxygen is the same thing. It's just oxygen gas. But when it forms a metal oxide, oxygen almost always becomes -2, which means your metal, in this case, would become +2 if it's a 1-to-1 ratio of the metal oxide forming. So which one got reduced and which one was oxidized? Well, metal became a metal 2+ by giving up 2 electrons. Is that an oxidation or a reduction? That's an oxidation, right? It was oxidized. That's why we call this oxidation, right? Metal oxidation. And your oxygen gas picks up 2 electrons to form oxygen 2-. So it's actually reduced, right? Or oxygen is the oxidizer, okay? Because it oxidized the other thing. It caused the other thing to get oxidized, okay? So when does this happen? How does this happen? There's a couple ways that it can occur. Let's say we start out with metal, okay? You got a block of metal, and you've got oxygen gas out over here. So right as soon as you take it, like whatever this pen's made of, I'm sure it's aluminum, right? This metal is exposed to oxygen. Now, if I looked up in this table, do they have oxygen on here? Kind of. This is all aqueous. But if you looked up the reaction for aluminum and oxygen, and you added together these two half-cell reactions, you would find that the formation of aluminum oxide on the surface is extremely favorable. So why it is, maybe you've seen aluminum oxide before. What does it look like? It's like a white ceramic, right? It's brittle. It does not look like a metal. And yet I've just told you that aluminum metal in contact with air should be turning into aluminum oxide. So what's happening here? This should be puzzling to you, right? Are you puzzling? Right? So what's happening is this. It forms a metal oxide layer, which is, once it forms, it basically blocks transport of oxygen or metal. Or in other words, in order for this to keep on growing, for this oxide to keep on growing and converting your pristine metal into metal oxide, which is not usually what we want to happen, you have to have one of two things happen. You can either have oxygen trespassing the oxide barrier to access the metal, right? Oxygen would have to turn into, say, oxygen 2- and travel through this oxide to get to the metal. Or you could have metals trespassing the barrier, metal 2+, moving through that barrier to reach the oxygen, and then it could grow that way, right? Either of those things happens, and this thing keeps on corroding until it disappears. And what's amazing is that aluminum really wants to form this oxide, but it forms what we call a passivating layer. A passivating layer. It's such a good blocker for additional ion transport. Transport just means movement. Like you can't get metals across it, you can't get oxygen across it, that it passivates it. Once it's formed, you have no way, even though thermodynamically this still would love to react with that, they can't get to each other, right? This is the same reason that we paint surfaces that we don't want to corrode. If you don't want corrosion to happen, you paint it, right? When you paint it, you're not keeping the water out. That's the common misconception. People think that by painting it, you're blocking the water from getting to the metal underneath it. Water's a tiny molecule, and paint is made of big molecules, so it can slip right past them. What you're blocking is salt ions. And if salt can't get across it, then it can't corrode, right? That's your salt bridge, basically. And if you block the salt, then you've protected it from corrosion. So this is metal oxide formation. So how do you know some metals, like aluminum, are amazing, and they form these naturally passivating layers? And until you scrape it off with like some steel wool, that layer is just going to protect your aluminum, which is why we don't have to paint aluminum. This is all aluminum, and it's not painted or covered in epoxy or anything because it has its own natural defense against further oxidation, which is pretty amazing. Pretty amazing. Meanwhile, other things like iron, if this was made of iron, right, over time that would turn into the ugly rust color that we've seen old cars and pieces of metal turn into, right? Water can make this happen faster because it allows salt. It intermediates that exchange of electrons more easily, but it will happen in air all the same. Yeah, Alex? Why can't you see it? It's super, super thin. Because it forms such a good passivating layer that just once a little bit grows, really, really thin amount, it's enough to block it. If it grew at all thick, you'd see it. It's a big white layer. But because it's super thin, and I don't know the number offhand, but it's going to be very thin, you don't see it. Okay? Yeah, question? What's your name?
I'm Levi.
Levi.
I was just going to say, you can see it. It's the reason that it's not shiny.
Yeah.
So most of the time, aluminum that's like super shiny has just been polished, and we just never see that because it always oxidizes. And so it comes out as that kind of matte, whitish finish.
Metal rainbow, what's the word I'm looking for? I don't know what's going to come up. It's always dangerous to Google image in front of the whole class. But if you've seen metals, this is not what I'm looking for. Okay, like this. If you've seen welds, has all these funky colors when you weld things. Maybe you've seen this before. What you're seeing is not the color of the metal. You're seeing a very thin, even though when we weld, and we'll talk about this later, you use a cover gas like argon to prevent it from oxidizing, right? If you push all the oxygen out of the way and you flow something really inert like argon, then there's no oxygen for it to react with. But no welder's perfect for doing that, and so there's always a little bit of oxygen. And what you're seeing here is oxide layers forming on the metal, and they're forming thicker in some spots and thinner. And basically, the color that gets reflected is a function of how thick that oxide layer is. So when you see all these funky sort of colors on welds, you're seeing oxidation, evidence of some regions of oxidation that are different than other things because the temperature was slightly different or the gas pushed it out of the way slightly different. But that's what you're seeing. Yeah?
So like, will machined aluminum not be, so does aluminum grow that layer back, say if it was machined?
Yeah, very, very quickly. Because the driving force for it is, I don't know the number, but it's going to be very large, a few volts basically. So it has a very strong affinity to form that oxide layer. So essentially immediately after you machine it or scrape it or whatever, it's going to form a new layer. Which is nice because not only does it protect it from future oxidation, but aluminum oxide, which we call alumina, is extremely hard. It's a very hard coating. Ceramics are harder than metals. And when you have a nice thin coating, it actually puts like a really strong skin on it, which protects it from abrasion. Anyways, it's a great material. Now, this pen, ever seen that like new iPhones and stuff have like this sort of really dull, it's like a matte colored aluminum, more so than like this slightly more shiny version? This is what we call anodized alumina, or aluminum. What does anodized aluminum mean? Anybody know what this is? Yeah, you have a thought? So it's not sandblasted. That's what it looks like. It's not, though. Good guess. It's slightly different. What do they do? What does anode mean? What have we learned about in this class? Anode means that an oxidation reaction took place.
It's when you're applying a voltage to it.
They intentionally they apply voltage to this to grow an oxide layer. Meaning it's going to form its own oxide layer, but if you cause one to be grown really rapidly, then you form this. You form this. You've got your metal, and now you're going to form an oxide layer, and you grow it so quickly that it's kind of Swiss cheesy. There's bits of holes in it, and you can fill these full of dye molecules. So if you've seen fancy MacBooks or iPhones or whatever, and it's metal, but it's also green or pink or whatever, the green or pink or whatever colors are living inside these pores because they intentionally grew this layer to be large. Now, there's lots of ways you can do that. You can do the oxidation in the presence of an acid. So the acid is etching this layer away, but you're also growing new one. And so you can grow really thick protective layers here. And then because the acid has been etching it away while you did it, there's a pathway to put dye molecules in there. It's pretty slick. This whole process is exactly the stuff we're talking about in this chapter. Using corrosion, instead of just saying we live in a world where corrosion exists and that sucks, you can use corrosion. You can use these reactions to know what voltages or combinations of things put together to make sweet devices like anodized alumina, which is pretty rad material. Okay? Now, how do you know whether, like, aluminum does this but iron doesn't? The way that we calculate it is something called the Pilling-Bedworth ratio. Basically, if the volume of the oxide, the metal oxide that forms, is a different volume than the metal underneath it, which it came from, right? That metal underneath turned into the oxide. And if there's a big difference in the volume, then you're not going to get a nice passivating layer. You're going to get one of these two scenarios. If it's the same, imagine this all used to be blue, and then we oxidized it, and the oxide is this nice gray layer. Well, everything that used to be blue turned into gray because it's the same volume. It just converted from one phase to another, right? So this is just fine. This would be like aluminum. It passivates it. It passivates the rascal, right? Over here, if the Pilling-Bedworth ratio is less than 1, then that means that the volume of the oxide formed is a little bit less than the metal that it came from, which is going to leave cracks. It's like Swiss cheese, right? It's going to leave holes, and in those holes, more oxygen can continue to access the surface of metal. So this will keep on corroding, right? This one it will not passivate. It will just keep on corroding. And meanwhile, if the oxide that forms is bigger, right, if it expands even more during this conversion, then these things want to swell, but there's nowhere for them to swell, and so instead they buckle, and they chip off, they spall off. Spallation, that's what this is. So either of these two scenarios will keep on corroding until they disappear. So you can do the math. You can calculate what's the ratio of iron oxide to iron metal, and you're going to find that it's not between 1 and 2 probably. It's either smaller or larger. I don't remember which one it is. But that's why iron continues to corrode, turning into rust and ruining your devices, right? This is pretty slick, right? Any questions about the Pilling-Bedworth ratio? Yeah, I don't remember your name. Jaden.
So this second example where it's like higher than 2.
Okay.
So like you're saying, can you explain that again? Why they're buckled?
Yeah, okay. So in all these cases, imagine you start out with a nice blue rectangle of metal. In this case, when the metal converted to metal oxide, because of the crystal structure, which we will learn about in 3 chapters, the final product actually shrinks in volume a little bit. And because it shrinks in volume, that leaves openings, like Swiss cheese. Meanwhile, over here, the final product actually expanded, which makes more intuitive sense if you're adding oxygen to something, the same number of metal atoms, but now you're just adding some oxygen. It's more intuitive to think like, oh, that's going to expand and want to swell. But if it's confined on that surface and you're making it swell, it can only grow so much before it will buckle. There's going to be a stress that forms as you convert more and more to the oxide. So that stress, depending on your material, might be large enough that actually causes these things to debond, right? Which is when they're flaking off. When they flake off, that's why rust. So rust must, I'm guessing it's going to be this one, because if you touch rust and you like drag your finger along it, you're dragging bits of it off, right? It's not like it's still bonded, but there's channels. It's more like this. So I would guess this is what's happening with iron and iron oxide, but I'd have to check it. Any questions about this? Let's keep going. We're almost out of time. So the rate at which this metal will oxidize will change depending on which one of these three scenarios you have, right? So for example, you're going to get linear growth of the oxide, meaning it's going to just keep on gaining weight. If you had this thing on a scale measuring it, it started out weighing, let's say, 1 gram, but as it oxidizes, you're not losing metal. It's that oxygen is joining you. So if you weighed this thing, you would literally see a weight gain over time. As you slowly add oxygen, you'd see a linear weight gain because it always has a pathway for more metal to show up, right? This thing is going to be an asymptote really quickly. It's going to gain weight initially really quickly, right? If it's like aluminum, it really wants to form that oxide. But once it forms it, it's going to protect it from further oxidation, so the weight gain is going to drop off pretty quickly, right? So you can look at the rate at which weight is being gained, and it will give you some insight to the type of corrosion mechanism that might be taking place. Yeah, Zoe?
So if you were to completely oxidize the metal to have that source in the middle, we had a metal that was in the middle and we just added more oxygen.
Yeah, like anodizing alumina. Aluminum metal wants to be this, but you can make it into this one, doing anodized aluminum. Yeah. Now, the way that they do anodized aluminum is they apply an acid, basically. And the acid starts etching things away, and that keeps on growing it. But yeah, that's what happens. So the final version of anodized alumina probably looks less like this and more like there's canyons from the acid, right? But the bottom layer doesn't etch all the way through. And so that forms like a nice, solid, impermeable layer which protects it. But you've got the regions above it that you can put dye molecules. Plus, remember, this outer layer in aluminum oxide, this stuff out here, that's your really hard, strong layer. So it makes it more scratch resistant because you built up a bigger ceramic layer on it, which makes it more scratch resistant, which is nice for a lot of consumer electronics. So we're out of time, but what we're going to do is the following. I'm going to write down, these are available, additional practice problems. I'll give you a couple days, and then I'm going to post the solutions to these. But I would say give them a shot. Take them to the TAs. If anything wasn't clear from this chapter, work through these with the TA, and then I'll post the solutions later. So no class on Monday. Come on Wednesday and be ready for the coolest demo of the entire semester.